left support, fixed support, and then middle support. Okay, you have rotational spring on the 4th degree of freedom. You have the vertical spring on the 5th degree of freedom, and you have the free rotation end. Okay, at the 6th degree of freedom. That's the example you've seen on that day. All right. Again, fundamentals. You start from your stiffness matrix, okay, from element, and then you have two elements, you add them up into one stiffness matrix, okay, system of equation here. All right, then I erase this part down. Okay, so we are here. We are not going to erase or eliminate any rows and any column. Okay, we will do this change, okay, or move these three folks, all right, onto this side. Okay, so wait, okay, this is your original matrix. That's the K that I put there, right? So the original matrix will be the combined one. Anyhow, you need 3 additional columns, right? 3 additional columns because you are introducing 3 support boundary conditions and also 3 rows. And then I put 0 at first. Okay. Basically, as I show you this one here, that means your homework number 8 will be automatically this homework, which is conducted by the technique Lagrange multiplier. Okay, so that's gonna repeat last time homework, but with this one, at least it just bring you through the scheme. Okay, and then you will learn. All right, then I move this part back to here. Multiply. But the point is that your F1, F2, F3 will be moved from here to here. Okay. So in your unknown vector, which it used to be just the displacement unknown in the past, alright, so now your unknown has become you have the force, okay, the alien species coming into your unknown vector. Okay, so this alien species will be where? First of all, you talk about F1. F1 is here, so it is associated with this location. It is in equation number 1, which is the first row. Okay, so you have -1 there. You have F2. F2 has to be here, so -1 here. And F3 -1. I am not just simply putting it here, 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 put it like diagonal, beautiful like that. No, I look into first, this is relevant to equation that governs the degree of freedom number 1. So it has to be in this first row. It has to be in this column because it is associated to F1 here. Okay, so this is the idea. Okay, I'm not just putting things in there, put it inclined like this and then it's gonna work. So next time you might end up with this situation like -1 could be here, for example. Okay, it depends on how the arrangement of your degree of freedom. Oh, by the way, Up to now, any question? I forgot. I finished all this explanation, talked about so many things I didn't ask you, okay? Is there any question? You want to you want clarification on anything, any point? Any?
No.
Still good for Lagrange multiplier? Okay. Right? Next, you introduce the force back into equations now. Now let's talk about the displacement equations. Okay, the boundary, the additional, we call it augmented equations. Okay, you have over here. So those augmented equations, first of all, you have the displacement u1. It has to be 0. Okay, so let's put it u1. This first column is associated with u1, right? So I have -1. On that side, on the right hand side, you will have a 0. So, okay. You have nothing to do with this one here. As it will be, okay, you don't have any support reactions, fixed end reactions coming into here. Alright, but on this side, let's see. On this side, you move F1, F2, F3 back to the left, so you have all 0. So this is associated to your equation. You have -0 plugged into here, and -0 here, and -0 there. So these three locations, these three DOF are support. And then -1 and -1. Okay. So what's the next step? You will have 1, 2, 3, 4, 5, 6 green and these 3. Okay, so this is equals to this one minus this one. Okay, right. It is equals to that thing, all right, the big part over here. So we're gonna solve for this unknown vector. Here. Okay. Your unknown vector here is equals to equals to mat multiplication of M inverse matrix of this guy, right, multiply to this guy So can you see here, let me highlight this off. This is U1, U2 and U3, okay? They are just 0, okay? 10 to the minus 18, 17, 0. You cannot end up with anything non-zero because you have three equations to say that this must be zero. So when you solve this equation and then you end up with something that is not zero, okay? Your solver or you have done something wrong for sure. Let's see U4, U5, U6. Let's see U4, U5, U6. Where are they? Point 0.06 minus 1 something. Why is it? Oh. Wait a second. It has to be 0 here, right? Wait. 1 second. I need to zero them off here.
No, sir,
Yeah, I need to zero them off here.
so it will not be 0, sir. You already subtract from previous.
It is lumped into that reaction. You cannot change the part. Any part. Okay. Oh, it is an array. Wait a second. 0, 0. Okay, so here this part is equal to this minus. To execute it. No, doesn't turn out.
Teacher,
Right.
the modified k that you copy is not it's different from
Which K? This one?
it's different from
This
it's
one?
not the same.
Not the same.
Yes, to
Wait.
copper value
Huh?
All the numbers inside here.
Inside this K.
is not
Not same.
Oh, this is.
Changed.
Oh, how's it changed? Okay, whatever. Then I got to minus equals to this. Thank you. Oh, that's a lot of change. Got to. Okay. So now you end up with this, which is equals to this one, right? Minus 104 minus 1815. Alright, these are 0 as you expect, and here are your reaction forces. But now you got to keep in mind F1, F2, F3 right now are not exactly the same as this one. 0.508, point something, right? Why? Because when I solve, I zero this part out. So if I zero this part out, what does that mean? It is the reaction. Okay, it is a reaction F1, F2, F3 with the minus 0.5, minus 0.833, and minus 0.75. So over here, minus 0.5, right? This is minus 0.5 is here. Okay. So basically, I move this to the other side. Okay, I move this part to the other side, and then I solve for not only just this one. Okay, let me write it down here. Minus 0.5. Okay, when you change from that top, from this equation to this modified equation, Okay, so I push this, oh, maybe I should keep the F1, F2, F3 here first, okay, and then come to, oh, it cannot be done that way. Okay, so I just put it this way. Minus 0.0833 83 and then minus 0.75 in there. Okay, so you are solving this or that is going to make here plus 0.5, here plus 0.0833, here plus 0.75. So we should end up with this, right? Okay, so you can see a good match between this reaction force from the row and column elimination scheme and the Lagrange multiplier scheme. Okay, so we have no room to come up with two different solutions from two schemes. They are just different mathematics, but mathematics always consistent. So if you do everything right, then you will end up with exactly the same solution. Okay. So as of now, do you want any clarification? You want another time of explanation? Another round? Okay, another round. So I am here. Okay, I set up the system of equation for your standard practice. Now you've got the system of equation, but you will need additional rows and additional columns to introduce your boundary conditions. You know that you have 3 boundary conditions. Those springs will be in here already, right? So you don't need to do anything with it. But over here, additional rows and columns are for the support. And these 3, okay. First, you move this unknown part, okay, which are the support reactions, from one side on the right hand side to the left hand side. All right, so should I just do it this way? I will copy this and insert copy cell. Values and formatting. Okay, all right. I made it like this first. Okay, so you have this equation. This equation I will have the F1, F2, F3 keep over there because I'm gonna only you can go back and track from this file. Okay, so I think it is step by step. Okay, so the first step you have the assemble matrix. Okay, you just consider the green cells now. So first you have the green cells. Okay, stiffness matrix multiplied by the degree of freedom, displacement degree of freedom, and then now you have the fixed end reaction. Okay, equals to the external force. Okay, same old thing. You work on this, you know how to come up to here. So these are unknown from support. These are known from point, nodal point that you apply forces and moment. To change from this line, okay, this equation to this equation, you do not like to have F1, F2, F3, which are unknown on the right hand side. So you want to move it together with their family, their unknown family. The thing is that what I did over there, okay, I move this also to the other side. Okay, but when I move this to the other side, I find that these known values will go with the unknown values. Known plus or minus unknown turns out to be unknown. What is unknown anyway, right? So you have 100 plus unknown. It is unknown. Okay. So I treat it like the unknown, the whole thing like the unknown. But okay, I will show you how to make it another way around. Okay, so I put them together like this. Okay, so bring these reactions, okay, effects to this side on the unknown side. But okay, keep in mind that it is the unknown reactions, and then add up with the effects from the fixed end reactions. Okay, so you zero this out. Okay, you add the -1, the first -1 for this equation, saying that you have the effects from stiffness and displacement. Okay, the K times U, and then finally this part here. You move the F from the right hand side back to the left hand side. So this one is multiplied to -1. Okay, it is moved from the right hand side back to the left hand side. Likewise for equation number 2, you also move the unknowns from the right hand side backward to the left hand side. So you have the F2 multiplied by -1 on this side, okay, and F3. And then you introduce the displacement, the conditions of your displacement. So you know that as these U1, 2, 3 are at the support, you need the zero displacement. You have zero displacement, then U1 multiplied by -1 must be equal to 0 on this side. Okay, U2, okay, equals to 0, and U3 equals to 0. So you enforce the known boundary condition in these 3 equations. Now you solve for it. Okay, you solve for it, you get the first 3 degree of freedom turns out to be 0, okay, as it should be. U4, U5, U6 are determined accordingly, alright? And then F1, F2, and F3, okay, determined. But you keep in mind that these unknowns are the mixture of the reaction force and the fixed end reaction. So you need to clear out the fixed end reactions of that 0.5, 0.083, and 0.75, push them back to the other side, you end up with F1, F2, F3, like so. Okay, this is Lagrange multiplier option 1. I can do the option 2 for you. Option 2, what if you don't want to bring this all together to here, okay? So let's say you still want to solve for only F1, F2, F3 being the reactions, okay, without that part. So I don't clear it off. I will still have okay, wait. Fill without formatting. Okay. So minus 0.5, minus 0.08, minus 0.75 are brought onto this side. But I don't move it along with the F, okay? So if I don't move it along the F, then over here, maybe this should be the option that is more friendly to you. So I don't have this line. Everything will be automatic. So when you solve, you end up with F1, F2, F3 to be this value automatically. You don't have to bring back the minus 0.5, minus 0.08, and minus 0.75 back to that side. Okay. It can be done in many ways. Maybe this one is more friendly to you. It doesn't confuse you much. But the whole point is that you are moving things around on the left and on the right. Okay, back from left, from the right part of the equations. But as you know mathematics, I think it is still logical, and I don't believe that you should memorize how to use this scheme. Okay, I like you to try to understand and treat everything like a mathematics. You are not treating things like this is the Bible and you need to follow this Bible. You don't need to go that way. I think my second round explanation is not better than the first round. As my energy is running out more than the first round, I have the declining energy for now. So my brain is not trying to do things that good, okay, that well. But anyhow, any problem at any point, it is your shot to ask. Okay, please ask before we move into the programming. So, okay, we start from this point. Which location in this spreadsheet confuse you? I can try to explain for another time. Nothing? If yes, go ahead. Before we move, we're gonna move next to the programming part for the MATLAB. So more things. You don't need to leave any doubt behind.
So what was the difference in setup? Then option 1?
Option 1 and 2. Ah, good. Option 1 is the more confusing option. Okay, that's it.
I didn't follow what you did in option 2.
Okay, the difference. Actually, if you don't want to confuse yourself, you just stick with option 2. Maybe that is better. Option 1. Okay, option 1. F1, F2, F3 is here, and then I move this to this side. Alright, I move this to this side. So you will end up with F1 minus 0.5, F2 minus 0.0833, F3 minus 0.75. When I move the whole thing to here. Actually, option 1 is quite friendly to the computer. I move the whole thing to here. So that means I zero it out, okay? And move also this to here. So your unknown is not just reaction F1, but your unknown is reaction F1 minus 0.5 that I move. It stick together. I move the whole entry to here. So in that option 1, you have F1 minus 0.5, you have F2 minus 0.833, you have F3 minus 0.75. So when you solve and you come up with F1 minus point that, F2 minus point that, and that. But here, I leave these 3 things over here. I don't move them along to there. So once you finish, you solve, you get the result. That's why you don't have to do anything further, because your F1 is just F1 alone. It is not F1 with the minus 0.5 and so on. But in the computer programming, sometimes it is easy to just zero out that 3. Okay. So sometimes when I program by option 1. I didn't program by option 2. But it is just 2 different possibilities. It's just mathematics. So one way or another, and then it will bring you back to the same solution as far as it is consistent. But that's the only difference. But option 2 should be easier to understand for you in general. Okay. Right, so in your homework, you can go with option 2. Okay, if you want. Then, we have another possibility. What if I want to enforce the boundary conditions by many different techniques in one problem? For example, I want to enforce. We have 3, right? So why don't we do 3 possibilities, 3 possible techniques in just one problem? So degree of freedom number 1, I will use row and column elimination. Degree of freedom number 2, I will use the penalty method. And degree of freedom number 3, I use the Lagrange multiplier. That would also work because it is just the treatment that you apply on just one individual degree of freedom. There is nothing saying that if you put number 2 by penalty, you put penalty spring there and then you will not be able to use other technique. The thing is that you need to be consistent. So if you use the number 2 penalty for number 2, then you got to look onto the force side of number 2, and then those force in number 2, reaction force in number 2 will be just automatically taken care of by the spring, stiff spring. So sort of thing like that. But you cannot treat the boundary condition by using more than one technique in one degree of freedom. So you want to use the penalty spring and row column elimination in the same for the same degree of freedom not possible, or penalty spring and Lagrange multiplier in the same degree of freedom, that is not possible. All right, 1 degree of freedom you assign one technique there. So another one, just so let me call it what? All hits, right? Okay. It's like a album for all hits.
Songs.
Yeah, for songs. Okay.
Homeworks will be continuing previous. So homeworks 9 would be the continuation of the homeworks 8.
Or 9? Oh, we have 8 already, right?
Also, sorry, 8, sir.
8. Yes, will be continue from the 7. Yeah. So you have the same problem, but you do it
Like this.
Different method.
like using the Lagrange multipliers technique. Okay. So. Clear off the border. Okay. Now, the green is your original matrix. What do we want to do? U1 by row and column elimination. So I eliminate. Let do it this way. I copy it down to here, and then values and source formatting. Okay. So eliminate this. I delete the entire column by shifting cell left. Okay. And I delete the row.
So can you just make it a little bit zoom?
Oh, you need bigger? Yeah.
So for our recordings.
Yeah. Okay, thank you. Yeah, just let me know. So, okay, I delete the row. Shift cell up. Okay. Now, row and column elimination for U1 is done. How's about U2? You have these values. So I add the stiff spring to this entry. Let's make it 8, 1, 2, 3, 4, 5, 6. Okay. What else do I have to do? Using penalty method, you wouldn't supposed to have F2. You don't have external force, but you have spring force instead. Okay. But you still have your U2. Okay? It's non-zero. Now, I use the Lagrange multiplier for U3. So for U3, your F3 is here. I zero F3 out, and then I invite F3 down to here. Okay. F3 is here. F3 is associated with this row. Okay, this row for equation number 3. For equilibrium along the U3. So get the -1. On this side, well, as it is a support, here is 0,
Minus.
here -1. Keep in mind that your matrix was eliminated, so row and columns are eliminated. Okay. So you used to have this one, okay, the big one. I make it like this, so you still have idea that this happened. Then you know that this -1 is in the third row, okay, for U3, and this is on the third column. We just eliminate the first, okay, but okay. Just that, right? So I have the right hand side. 1, 2, 3, 4, 5, 6. And it is equals to 1, 2, 3, 4, 5, 6 minus is equal to this one times this one. So finally you end up with this one being this and this. Okay, you don't have U1 over here because your U1 has gone straight to the hill, so it's not appear up here. You have these two. First of all, U2 is almost equals to 0, but the U2 has been taken care of by using the penalty spring. The U3 was taken care by the Lagrange multiplier. So you don't have the reaction at U1. Okay, reaction F1 is not available because you use the different techniques to treat. Then you got to go back and then put all the U's you have and then in the equation such that you come up with the number 1 degree of freedom reactions. For U2, if you want to get the F2, you end up with just minus this multiplied by this thickness, okay, which is the thing that we expect. For F3, you get it directly over here because you use Lagrange multiplier, and then this 3 displacement. Okay, so you can do the all hits in one problem. Fine. Okay, just don't confuse yourself. You use one technique for one type. For example, if you use the penalty methods over here, but you still carry the F2 over there, then okay, you confuse yourself up, right? You use Lagrange multiplier and then you add big spring there, okay, that's gone crazy, okay, so just need to be consistent and you will find. And to be consistent, you need to understand, that's the point, that's the whole point, right? So you just cannot memorize the technique, the flow. You are not memorizing, you understand and then you can use it. And if you want to use it different way from here, but the mathematical justification is okay, then you are welcome to do, alright? It is the graduate, postgraduate study, okay? I am just telling you how to solve the problem in one way. So you can go with another way, another directions, but okay, considering your background knowledge in mathematics, all right, that you may have, okay, you can extend into any direction that you want, as long as you are not running against the science and mathematics. That should be it. Okay. Not the right timing. So maybe what? We can work on something. I'm gonna come back to Excel in a bit shortly. But okay, let's look at this problem. So the boundary condition techniques we have, okay, out of three, two of them you can introduce the displacement to your system, okay. So we call it prescribed displacement. Or rotation. You can prescribe, you need to move this much, okay? And then you analyze your structure according to your requirement. Two techniques, you can use the row column and you can use the Lagrange multiplier. Okay, so these two techniques will help you out in this situation. So for example, you are working in this problem, alright? For now, you don't have any force applied. You want to apply the displacement at nodal point, for example. So, what can that be? Maybe I want U1 to be equals to delta, positive delta. So let me say that I'm gonna displace this up by delta unit displacement. Okay, what will be the corresponding forces that is caused by this applied delta? Now you don't apply force, okay? Now you apply the displacement. You control the displacement. So let's first start from the row column elimination. You have the stiffness matrix of this one. EI. Oh. Okay. No distributed force, no span loading. So you don't have that friction reactions in this case. You can add in if you want, okay? It is nothing, you just have more vector and then you put it there. Okay, I put it there. Otherwise, I don't show you this and then later on I put it there and then you get confused again. But again, it is just a mathematics. So let me put this W. So you have WL over 2, WL square over 12, WL over 2 minus WL square over 12. This is the fixed end reaction, okay, associated with the uniformly distributed load, right?
Sir,
Yes,
if point load is loaded at a mid-span,
yes.
then what will be the effects in this case?
Okay. If point load is on the mid span, okay, what's gonna happen? You can do it by two approaches, okay. First approach, if you want to make your life really, if you don't care about the number of degree of freedom, okay, then you add one more degree of freedom, two more degree of freedom there, okay. So you have 1, 2, 3, 4, 5, 6. You can make it 6 degree of freedom problem. That is one option. And then if your point load is no longer at the mid span, it is on the nodal point. Okay, so this is one way. Another way, you can find out the fixed end reactions according to this point load. Okay, so this is your point load. You have the A, you have the B. All right. Generally, you can find this and this. And basically on the back of your textbook, I'll also say that this is like PB square A over L, P A square B over L, and the reactions is how much I don't remember exactly. If you want to remember exactly, you can try that derivations. That will work. So go back to that moment area technique, find the deflections, rotation, whatever, and then you can come up with this fixed reaction. It is just the case that I didn't assign you as a homework, but basically you should try to do it. Okay. If I assign you a homework, oh yeah, let's do it, add it into your homework, then your friend's gonna hate you, right? So I don't do that. Ask him. Don't ask. Right? Your friends will try to stop you in the next time. But that is good. So you can check this out. Okay, you can find fixed reaction, and if you want, you try this case. It doesn't take long time. Okay, you can try, and then you can get the all support reactions that will be used. Then you don't need to introduce more load at this point because you don't need to have extra degree of freedom. You run all the calculations based on these two nodes, okay, and then these effects will be going to the nodal points by this treatment. So you have two options. Likewise, in structural analysis program like SAP, like whatever, ETAPS, the stat probe, you can do this. So they have the options that they can take care of the load being on the span, or you don't want to do it that way. You chop your element down to the maybe 4 or 5 elements, and every point that you apply load, you assign the nodal point as a degree of freedom. So you can work on it in both ways. But when the problem is small, it doesn't bother you. Okay? When you are dealing with larger and larger structures, and then you have these point loads on everywhere. For example, if you have like a building, and then on your building you have the main beam, and then you have the sub beam resting on your main beam, and then you have like quite a big building and then multi-story. So sometimes you don't want to know displacement, rotation over here at this point, right? You don't know that effects, then you just treat it by that way, that you don't introduce additional degree of freedom. Do I clear your doubt? Yes or no? If no, then I am glad to talk about this.
And after then the in equation.
The top one, you are not dealing with this equation. The top one, you will have the system of 6 by 6. Okay, 6 by 6. Let's forget about this one. Okay, let's forget about having this load distribution. Okay, maybe we have just this point load on this band. Okay, so the first option, 6 by 6. Do we have any fixed end reaction? No, because the point force is applied at the node. So you don't have this fixed end reaction, so it is 0. On this side, it is 0 everywhere, but at this, okay, you have the point force here. Now, on the other way around, if you use the fixed end reaction for this point and you don't discretize your structure, you don't add the node over here. If you don't have the node over here, your system of equations still remain 4 by 4. But the point force will be taken care by finding these equivalent effects, okay, of the support reaction. So support reactions now is non-zero. Okay, now you have the moment and the force that is associated with, that is equivalent with this case. On this side, you have 0, right? Because you are not introducing this force at these 4 nodes. So you have 0 on this side. So it is different. One way, you have the point force introduced here. Another way, you have fixed end reaction introduced here. Either will work. Okay, all right. Let's see for here. But I think this is quite a very good thing. Okay, add this to homework number 8. I think first thing, you are in the school, the mindset about homework is very important. If you have the mindset about homework just to finish it up in order to get the grade, that mindset is gonna kill you. Okay, when you do things by setting it like, okay, I hate this, okay, homework, okay, and then you associate the unhappiness with homework. Okay, if you do that at first hand, you will not live your life happily. If homework is something that is the must, all right, it will be with you for this year, this whole year, all right? Then setting up that sort of mindset is going to kill you, because you will first, at the moment I say homework number 8, homework number 9, you feel like, yeah, that's something that I have to fix, and then I just want to get it done, and then I go back to my entertainment, Facebook and online movies, book is wedding, all right? So that is the wrong mindset. the appropriate mindset, because you are here to learn, to convince yourself in many cases, to educate yourself. So homework is something that will lift you up. It will elevate you from the undergraduate student to the postgraduate student. Okay, it will equip you with the confidence. I talk over there. I say that okay, these two cases are equivalent. Oh, it is equivalent, but at one point you feel sure or not. Sometimes he might not be correct. Well, at this point you might feel okay, I just believe him, but it is not convincing. Okay, one time if you get your hand on this thing, all right, you solve by having two nodes, and you solve in comparison with the three nodes. Okay, one element and two elements, and using fixed and reaction in comparison with having setting this as the nodal point force, and then at the end you end up with the same solution. Okay, displacement solution, the same, support reaction, exactly the same. That will be happier for you. So homework is something that you spend time just relax. Okay, don't stress yourself out at the first moment that you are not a Formula 1 driver that you just need to finish homework as soon as possible. Okay, you are not trying to drive and get into the destination at the shortest time. Okay, you are not Formula 1 driver. Just keep that in your mind. So you don't need to just get it done. Okay, if you think of homework just to get it done, if you think of it as a burden, if you think of it as okay, just gosh, I don't want it like that, you will not do it happily. Okay, but when you do it very happily, I can see from your work, okay, you feel very good about it when you work on it. Okay, it is reflected into the quality of your work. Okay, organization and everything will look like so smooth, and you feel good, right? And your mental health is good, you live longer. Seriously, when you put stress into yourself, you have adrenaline, you have some bad enzyme, hormone, oxidants, substance, okay, all bad things come up. But when you have a good mindset on anything, on the study, you come to the class, you wake up in the morning, I don't want to come to the class. But in comparison, you wake up in the morning, yes, I want to rush to the class. I have nothing to do. I want to come. I have fun coming to this class. That is totally different thing. And you will be just a happy and unhappy person are just separated by this sort of mindset. And mindset is something that you can set. So it's called mindset. You cannot set up your life. You cannot set up this class. You cannot tell me to teach what you want, because I'm teaching according to the curriculum that we consider that it's gonna be the best for you. So you cannot control me. You cannot say, sir, today I'm not feeling good for homework. Okay, can you just don't give me more homework? So whatsoever is uncontrolled in your life, use the mindset. Okay, you will be confronting with more and more, okay, harder and harder situation in your life. Okay, this is totally not about structural analysis, but believe me, you just listen to this, and one day, if it is applicable to your life at any certain level, okay, I'm not teaching you the religions, okay, this is not about Buddhism, this is not Christianism, and not about any religions, okay, in the world, but this is just the way to live your life very happily, okay? So if you feel happy with something at the first hand, okay, you will be doing it well. You love it. You are not you don't feel any pain when you write your homework. Okay, it is totally different, and of course different. We have different people in this room. Okay, many feel sad, feel anxiety, feels. Well, we have anger and everything, tough feeling shown in homework. Some it's like listening to the Mozart music and then do homework like that. Okay, I can just one day blind the name and then you compare these two sets of homework. Okay, you are listening to Beethoven and another is Mozart. Okay, very fierceful, very angry. Get me out of here! I don't want any more of this. Okay, and oh, what a beautiful life. Okay, I'm sure you are not up to the point that you can do, but you need to practice. One day when very bad thing hits you and when you think of it, like, okay, well, at least I learned something. You put some money into your investment on something you found a company, okay? Your first 2 million baht is gone, for example. Okay, I'm not saying that you're gonna hit that situation, but okay, some bad things happen to your life. Maybe your girlfriends cheat you, maybe your boyfriends break up with you, or bad things happen. It doesn't kill. I'm still alive. It's not bad. At least I learned something, right? And then your life will be packed with happiness. Sadness is just something you make it. Okay, it is synthesized. It is not real. Actually, in this world, there is nothing real, but science is real. Mathematics is real. Okay, but whatsoever going on in your life is not real. Okay, it is just something, and then you judge it. Okay, you don't like it, then you feel unhappy. But you have something, you look at it, and you don't judge it. You don't look at it and then make it sad to yourself, make it unhappy to yourself. Then you still feel okay, neutral, not bad. Just go ahead, fine. Do whatever you want, okay? This is the best part that you can control in your life. So try to control it. Okay? So I hope that you go back, smile before you do this homework. Okay. I found this thing when I was in high school. You know, I'm a scientist. I hate social science. Social science? What do we want? To learn about the history of the countries in European countries. Huh? In the Europe, in America, I don't care about Columbus. I don't care about Abraham Lincoln. Whenever they declare the independence, how would that relate to my life? I have no interest in that. Okay. So that's the pain. And then I figure out, okay, I cannot avoid this. I cannot tell the school to, I don't think this subject matters myself, right? Can you just do me a favor removing this from the curriculum? It's not possible to do that. I'm in the school, so I'm nobody. I just to take this course, whether or not I like it. So, should I sit there in the class, feel pain, feel very bad? Oh, believe me, the instructor is like very old-fashioned ladies dressed like Thai old lady, okay? Teach in a very old Thai style teaching, okay? So you can imagine how bad that was. The subject is not interesting to me. The instructor is really, really bad, okay? So that's the worst combination in life, okay? But but how to just get out of that situation happily. So just change the mindset. I cannot just fire her. I cannot remove this subject. So why should I sit in her class, feel pain, feel torture? I don't think that is good for my mental health. Okay. And not good for my academic records also, because if I hate it, then I will not get the 4.0 from that course, and then my academic record will not be good. So, well, just enjoy it, maybe. And then I just 1 point, click it like that, and then enjoy social science. Oh, well, yeah, boring teaching style. Okay, fine. I enjoy. At the end of the semester, I get quite a good grade. I still feel very good with myself, feel very good coming to her class, even though everybody is just, oh God. But I still sit there, look at her and, okay, well, yeah, I know this, okay, why not? It's not bad, it doesn't add me some burden, okay, so just learn. It is an art of living your life happily. So come back to this happy life. Here, support what equivalent reactions. Okay, your stiffness, this part here. What do I want to do to show you? I want to introduce the U1 equals to delta. Okay. Well, knowing that U2 is 0. Knowing that U3 is also 0, okay? So if you want to use row and column elimination, okay, your U1, knowing that it is equals to delta, how do we do? You cannot, as U2 and U3 are 0, okay, you remove these 2 columns, right? Because these 2 columns will be multiplied to 0 value, so you don't like them. But the first column will be multiplied to hair coming into the mouth. Okay. So this multiplied to delta and this multiplied to delta, right? So you have the known value. Okay. So multiply delta to here, multiply delta to there, you end up with known value. And then you can bring your delta to this side and that side, the value that is multiplied with the delta. Okay, so what do you have? But still, you multiply to the delta, but you will not like this row. Because this row, you will have the F1. You have F1 because you want to push this node upward by delta, right? You need force, and this force is the F1. So you don't want it. So what do you end up with as of now? You have the 4EI over L, U4. Okay, minus WL squared over 12 plus 6EI over L squared delta equals to F4, that is 0. Okay, you don't have externally applied force or moment at that degree of freedom number 4. Now, these are known, so move to that side. Okay, so you can solve for U4. Okay, quite easily. So the fact is just that with the known displacement, you will distribute it into this stiffness matrix. You distribute into this stiffness matrix, you come up with the known value. So once you have the known value, you extract it off your stiffness matrix and throw it to the right hand side. So then you solve this system. Once you solve this system, you get the U4. You get U4, you can come back and find F1, F2, F3 accordingly.